Now that we've done some calculator practice, let's talk about some words of caution about interpreting confidence intervals. Remember the appropriate interpretation of your confidence interval. What not to say. We do not say 90% of all of the subject scored between 7 and 9 on the depression test. A confidence interval is about the population mean and not the individual data values. It is not individual data values. Another common response people have, we are 90% confident that a randomly selected subject will have a depression score between 7 and 9. Again, the confidence interval is about the mean, not individual values. So make sure you're talking about the population mean when we're talking about confidence intervals. A couple other things that people say incorrectly when interpreting confidence intervals are, the mean depression score is 8 90% of the time. Do not say this. The true population mean does not vary. The confidence interval and sample mean would be different from sample to sample. So the true population is constant. And that's what we're trying to identify, some range where it falls. Again, another incorrect, 90% of the samples will have mean scores between 7 and 9. 90% of all samples. So the interval we calculate does not represent any other interval. It is only one of many possible intervals and no more likely to be valid than any other interval. We're saying 90% of the time, or sorry, with a confidence of 90%, our true mean will fall between these two values. And lastly, do not say this. The probability of a mean score between 79 is 90%. Ugh. The interval we calculate is not special. The interval we calculate is not special. It is only one of many possible intervals and no more likely to be valid than some other interval. If you need the sentence, here's the sentence. What you do say, we're going to say, based on data from our sample size of, fill in n, I am blank percent confident, 90, 95, 99% confident that the true value of the population, where you're going to include the parameter and the variable, is between your lower bound and your upper bound. If we're saying C percent confident, we can also add, with repeated sampling, 90%, 95%, 99% of intervals that could be found from samples of size n would contain the true value. So we can use our conclusion from our confidence interval, and then if we are using C percent confidence, this is another statement we can make. As you guys know, and especially when it comes to means, we're going to need to draw a picture, draw a picture, draw a picture. Now you have another graph to draw. In addition to a T-curve, you must draw a histogram of your sample data to demonstrate the sample. And thus the sampling distribution is sufficiently unimodal and symmetric with no problematic outliers. You may also want to draw a normal probability plot to ensure that it is reasonably straight, indicating a symmetric distribution. So we should remember how to do a histogram based off of our sample data, along with a normal probability plot. Now, moving on to t-tests and hypothesis testing. Remember before, when we write out our test statistic, whatever it is, a z or a t, it's always the observed value, in this case it's our mean, minus the expected value over the sample standard error. So for a t-test, we use sample mean, which is usually x bar, minus our population mean, which is mu, over our standard error for the average x value, our random variable. And so you'll see below, we have t equals x bar minus mu over s, which is our standard sample's standard deviation, over the square root of n. And then we are going to indicate our degrees of freedom, which is always n minus 1. So a test for the mean. If we are doing a one sample t-test for the mean, the conditions for a one sample t-test for the mean are the same as for a one sample t-interval. Interesting. So if we have a t-test, they're the same conditions that we have for a t-interval, confidence interval. We test the hypothesis. So our null hypothesis would be that our mean stays the same for some statistic. Then we check our conditions, and when the conditions are met and the null hypothesis is true, this statistic follows students' T model with n-1 degrees of freedom. We use that model to obtain a p-value. So when we are testing a null hypothesis, just like we did before with a 1-prop z-test or a 2-prop z-test, we're going to give the t-value, always indicating our degrees of freedom. Do not forget to write a complete response. If you need your anagram, we have phantoms. So just to go over, P, define your parameter. H, formulate your hypotheses, both your null and your alternative. So your alternate hypothesis is what we are trying to hopefully show. Your null, again, means nothing happens. N, we're going to determine the test statistic that will assess the evidence against the null. So in this case, we're going to use the t-test as before we did a 1-prop or 2-prop z-test. Then T, we're going to find the critical value for our test statistic based on alpha. And we have to do a little work for that. O, we're going to obtain our p-value. That's where our calculator comes from. M, we're going to make a decision to either reject or fail to reject the null. And then S, tell someone about your results in context. So always interpreting what this means in context. So let's jump into an example. Say, for instance, the law firm of He, Ho, Hui, Quo, and Su are suing a bottle company for shortchanging consumers. He, Ho, Hui, Quo, and Su tested 18 bottles of soda pop and found a sample mean of 15.8 ounces with a standard deviation of 0.4 ounces. He, Ho, Hui, Quo, and Su is convinced the company is deliberately shorting the drinks that are labeled 16 ounces. Is the law firm He, Ho, Hui, Quo, and Su right? So let's jump into this. We do not know the standard deviation of the population of soda pop bottles, so we will use a t-test for mean volume of soda pop. The null hypothesis is about the mean volume of the soda pop, and we're testing to see, is it less than 16 ounces? Are we getting shortchanged? So our null would be that it's not less than 16 ounces. With the alternative hypothesis, or the alternate hypothesis, the mean value is less than 16 ounces. So here is our hypothesis. Before we jump in and jump to our calculator, we want to make sure that we check all of our assumptions and conditions. So, independence assumption. Well, we are not certain the consumers did not get all of the bottles from one distributor. So independence is questionable. But for our purposes, let's pretend it's okay. Randomization condition. We can be relatively certain that the bottles were randomly chosen based on marketing protocols. And then the 10% condition. 18 bottles is certainly less than 10% of the population of soda pop bottles. So that's definitely true. Next up, our normal population assumption. We have to check, is there a nearly normal condition? And it's a relatively safe bet that the amount of soda pop in 16-ounce bottles is normally distributed. To be confident, we would do a bar chart of the volumes in our sample bottles. We don't have this data, so we're going to have to assume a nearly normal condition. Once we've met the conditions for our t-test, we're going to jump to using our calculator. So we're going to go to Stats, Test. We're going to do a t-test. And what we need to type in is our mean, our hypothesis mean, which is 16. Our average, which is 15.8. Our standard deviation is 0.4. Our sample size is 18. And we're going to select, since this is a one-tailed test, if it's less than our hypothesis. So once we do, we get this data. We get a t-score of 2.12. We get a probability of 0.02. We get our average, our standard deviation, and our sample size back. Note all the useful information the calculator so kindly provides for you. So treat it nicely and keep it fully charged, and your life will be easy. Also note, we're not given the level of significance, so we default to 0.05. So a one-tailed test means all the critical area is below the mean. And if we do the critical t-test, which we mean the critical value for our t, corresponding to an alpha level of 0.05 with the degrees of freedom, we can use our calculator again to find that value, inverse t, and we're going to do 0.05, comma 17. You can find that under the distributions under your calculator if you're using a TI Inspire. Also, we're going to draw a picture. Draw a picture, draw a picture, draw a picture. With our shaded in region, we see that 5% are under. This is slightly past. We have our t distribution. The critical value of our test statistic of 5% in degrees of freedom is negative 1.7396. Once we have this, and again, just as our practice, we always label what our test statistic is, which is what our calculator gave us. So we're going to do this work by hand. So we have our t statistic with our degrees of freedom. Our x bar is 15.8. Our mean is 16. And our standard error is 0.4 divided by the square root of 18, with a degree of freedom equal to 17. So if we were to calculate the probability that the t statistic is less than negative 2.12, or the probability that we get an average that's lower than 15.8, or do a t-test, we would get the same thing we got before. So we have a p-value of 0.0244 with our test statistic of negative 2.12. Now you should all know what to do with that, but just in case you forgot, negative 2.12 is definitely less than negative 1.74, and a p-value equal to 0.017 is definitely less than 0.05. So our test statistic, or our t statistic, falls within the rejection area. The probability of getting a value of 15.8 ounces, if the null value of 16 ounces is true, is less than 5%. So our decision is to reject the null hypothesis. We must reject the null hypothesis. Since we reject the null, it is plausible to conclude that the bottling company is deliberately shortchanging the consumer. He, ho, hui, quo, and su has a reason to sue.